All right, we're starting here with 5.6. We're going to do the same thing, definite integrals this time with substitution, and then also look at the area between curves, which should make a whole lot of sense and really just kind of be pretty easy to do. It's just a matter of subtraction. So here for substitution, if G prime is continuous on the interval AB and F is continuous on the range of G of X equals U, then our integral from A to B of F of G of X times G prime of X. So the same thing as what we had for the indefinite ones. This time is going to equal here G of A to G of B F of U du, just like that. All right, so in other words, when we do this, you got to plug it in to figure out what your new limits of integration are. Your limits of integration are going to change as you do this. The other alternative to changing the limits of integration is to do it as though it was an indefinite integral, and then when you get it back to being a function of x instead of a function of u, then you do your limits plugged in. Okay, so it's kind of up to you, but here we're going to go ahead and just do it that way. So let's take a look at this one. We've got, and in fact, I'll even show this to you here real quick. So let's look at this first one. Let's do u equals x cubed plus 1. Then du is 3x squared, right there, dx. And so now what we can do is find our new limits. So we'll do u of -1, right? Because if we're switching from, whatever x cubed plus 1 equals is what u is going to become. So we put in u of -1 and we get -1 cubed plus 1. -1 cubed is -1, and so that's a 0. Then we'll do u of 1, and so that's going to be 1 cubed plus 1 equals 2. So that's our new limits of integration. So then our integral is going to become integral from 0 to 2, right? Here, the 3x squareds are going to cancel out, right? So I don't need to write them still, do I? Does anybody want me to? It's fine if you do. So the integrals are going to cancel out, or the 3x squareds are going to cancel out, and I will just have the square root of u, which is just u to the 1/2 du. And that's the integral then I need to do. So this becomes u to the 3/2 and then times 2/3, because it's u to the 3/2 over 3/2, which is, instead of dividing by the fraction, you multiply by the reciprocal, right? So that's 2/3 u to the 3/2, and we're evaluating it from 0 to 2. And so this will become, right? This will become 2/3 times 2 to the 3/2 minus 2/3 times 0 to the 3/2. This is obviously just 0, and 2 to the 3/2 is 2 cubed, which is what? 8, and then square rooted. So it's just the square root of 8. So this will equal 2 square root of 8 over 3. And square root of 8, we can make square root of 2 times 4, which is then 2 root 2. So this can also just be 4 root 2 over 3. Notice we have no plus c. Right? Whenever we do these definite integrals, because we would have had a plus c, and then we would have also had a minus c, right? It would have been like plus c right here and minus c over there, right? So the definite integrals, they are always going to cancel out. If there was a constant there, it's going to cancel itself out. whatever it is. It's always plus and minus. So there's our first way we could do this. What about, like I said, so this we'll call method 1, method I, method 2, if you prefer. All right, method 1, method 2 is going to be do the same thing. U equals x cubed plus 1 du 3x squared dx. So same sort of thing. Get that same integral, and we're going to do it as an indefinite integral. Square root of u du, 2/3 u to the 3/2, just like that. And then what we're going to do is substitute back in the x's. So this is 2/3 x cubed plus 1 to the 3/2, just like that. And then we're going to evaluate that from -1 to 1. So we don't have to change our limits. We still don't need the plus c because we know we're going to evaluate it. But now we go back to x and we can evaluate it over the range for x's. Okay, or the interval for x's. Here we end up with 2/3 of 1 plus 1 to the 3/2 minus 2/3 -1 plus 1 to the 3/2. So this term goes to 0 again. -1 plus 1 is 0. And then we have 2/3, and then we have 2 to the 3/2, which we just had a second ago, right? Which equaled 4√2/3. So you can see samesies, right? Y'all still say that? Nobody says totes my goats samesies anymore. Let's bring it back. I don't even know if I spelled my goats right there, but whatever. Or totes for that matter. Or samesies. No? I'm pretty sure this was the correct way. Besides, it's a small mind that can't think of more than one way to spell a word, right? That's what I tell myself when I misspell things. All right. Any questions on that? No? Try another one. Everybody said, yeah, we want to. So much fun. The level of excitement in here is crazy. All right, let's take a look at this one. In fact, recording. So there it is. If you're watching this later online, it's pretty simple. Just kind of look your way through it. All right, let's take a look at the next page where we can look at some symmetries for doing these. If you look there, you can see that first picture is a graph of a symmetric function. It's symmetric about the y-axis, which means it's an even function. If that is the case, then you see that on either side of the y-axis, the area underneath the curve will be identical. So if you're doing an integral from -a to +a, f of x dx, it's just going to equal 2 times 0 to a f of x dx. Right? Because the area to the right of the axis is the same as to the left. And so if you're being symmetric about the axis, you only really need to do one side of it and then double it. Okay? And if it's an odd function, like you see in the next picture, then we simply have to say, as long as you're going from the same negative to positive number, it's going to be what? Nope. 0. Look at that. All the stuff that's above is now below, right? Okay. So this one if you're doing this integral from negative a to a f of x dx, it's just going to equal 0. So if you see that one, and it's a crazy complicated one, then that's a pretty, pretty easy one there. Anybody remember how to check for even or odd functions? Can be, but not necessarily. Without looking at the graph. All right, even functions. F of negative x equals f of x. Plug in negative x into your function everywhere there's an x and see if it, once you square everything and cancel it, does it turn out to be the same as the original function? For an odd function, f of negative x will equal negative f of x for every x. So that's how you go through and check them. You plug in negative x for it, and you should get the same exact function, but with a negative sign out in front total. So, and then of course, if neither of those things happen, then it's neither, right? Like, so if you have f of x equals x squared minus 3, and you try f of negative x, you get negative x squared minus 3. Negative x times negative x is x. This is x squared minus 3. What do you know? That's an even one, right? But if you have something like, let's say we have f of x equals x squared minus 3x, and you try f of negative x, you get negative x squared plus or minus 3 times negative x, right? And then that becomes x squared plus 3x. What is that? Even or odd? Neither. Right? It's neither. If that had been an x cubed out front, then this would have been odd because everything would have had an opposite sign. Okay? So it's even, odd, or neither. So this one you're not going to have a symmetry for, but the other, but that one in blue you would. So let's take a look at this one here. Let's evaluate this integral from -2 to 2. Cool, we're going right around the so what do we want to check and see? Let's check and see if this thing is even or odd, right? All right, now I look at that and I say, all right, all the exponents are even. This is going to turn out to be even, but let's try it and see. So f of negative x is negative x to the 4th minus 4 times negative x squared plus 6. Negative x to the 4th is just x to the 4th, and negative x squared is just x squared, and the 6 doesn't get changed. So that's just our original function, right? Therefore, f is even. So, how big of a deal that is in helping us here with this one or not, I don't know, but we can do it. We can then say our integral can go from 0 to 2 times it, of x to the 4th minus 4x squared plus 6 dx. And that 0 is just a little easier to plug in than -2, right? I don't know if it's so much easier that it was worth checking it, but if you can eyeball these and you're certain if it's even or odd, then you don't have to go through that whole check process. But like I would have just eyeballed this one, or hopefully I would have noticed that this was even and done it. But otherwise, it's not going to be too huge of a difference. The one where it equals 0, that can save you a lot of work because you don't have to do anything. Sorry. So this becomes what? 2 times x to the 5th over 5. Oops. X to the 5th over 5 minus 4x cubed over 3 plus 6x. And we're evaluating this from 0 to 2. So this becomes 2 times, and then we're going to have x to the 5th, so 2 to the 5th over 5 minus 4 times 2 to the 3rd over 3 plus 6 times 2, and then minus 0. Because 0 to the 5th, 0 to the 3rd, and then just 0. Every term is going to be 0, right? So it's minus 0, minus 0, minus 0. Okay? So that's minus that whole thing is 0. And then you just have to go through and do this. So 2 to the 5th is what? 32 over 5. And then 2 cubed is, well, that's 2 to the 5th again, right? So 32 over 3, right? Because 4 is 2 squared. So that's 2 to the 5th again. And then plus 12 and all times 2. And so real quick here, just in my head, it's 232 over 15. Absolutely didn't think that out ahead of time yet. Don't come look at my notes. But common denominator there is 15, right? So whatever we get, 96, and then whatever the other is, something, 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 and then 96 plus 64, and then plus, what do we have to do? 12 times 15. I don't know. That's a lot of stuff. Yeah. Let the calculator think for you. I mean, if you had to, you could do it out, right? Hopefully. Okay. Any questions on that one? I guess I could put equals since he's actually equal. Okay. Good. That's okay with everybody. And then I think, what do we have here left? I'm going to let y'all work on this one for the last few minutes here, and then we will we'll be done there for today. So try and figure out what a U is. I'm not going to tell you, but take these last 5 minutes. That's what you should work on, and then we'll finish this up next class. Okay.